Good evening, everyone. My name is Aditya Sharma, and this is Power Plant System Engineering course being conducted, under the NPTEL program, being conducted under the NPTEL program and by Department of Mechanical Engineering, IIT Guwahati. Okay, so we are into the last week of this course, and the theme for the last from the last 2 weeks has been hydro and renewable energy power generation. So in that theme only this week's content is, and basically we will be discussing the energy storage systems in this week's content, right, and questions related to that. So the instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati. And I am also a research scholar here at Department of Mechanical Engineering, IIT Guwahati. So we shall then start with today's session. So in total, there are three lectures. So all three lectures are on energy storage only. So this has been discussed in three parts, right? Where in first part you focus on electric storage and electric storage systems. So there is pumped hydro storage system and compressed air storage system. Then in lecture 33 you focus on thermal storage systems. Okay, so be it pressurized water sensible energy storage or latent heat energy storage. Okay. Then in lecture 34 you have flywheel energy storage system and electric batteries. Then other few miscellaneous storage systems. All right. So this is about this week's content. So we will. So the content of the session is as has been mentioned in the this slide. Okay. So let's start with lecture number 32. Its topics. Then we will see its questions. Okay. So it has topics necessity for energy storage. So why do we need energy storage? And then types of energy storage systems, right? Then we have pumped hydro storage system and then compressed air storage system. These topics are discussed in lecture 32. So what is the necessity? So necessity basically is that at times, so we have some power plant system. At times the demand is high and at times the demand is low. Okay, so there are fluctuations in demand, right? And then if we are running our power plant at some specific load, okay, and the demand is higher than that, in that case you won't be able to satisfy that need, right? And in if the demand is low and we are running at high load, right, the available load is high and the demand is less, in that case there will be wastage, right? So what we do in that case is we store the excessive energy, and when the demand is at peak, we use this stored energy. Okay, so this basically is the necessity for energy storage. Right? Then is your, yes, energy storage systems. So in your energy storage, you have electrical, mechanical, energy storage, right? In this category, this is one subcategory. Then compressed air storage, sorry, in your this electrical mechanical storage only, you have one is pumped hydro storage, then is your compressed air storage. So this comes in your electric mechanical energy storage, right? Then is your, so I'm mentioning the energy storage systems. Then is your direct electric storage. Okay. So in your direct electric storage, what comes? You have batteries, then superconducting coils. So this is there in your direct electric storage, right? So these two come in your electric storage. Then you can store energy in the form of sensible heat, okay, in the form of latent heat, in the form of chemical reactions, endothermic reaction. In the form of endothermic reaction, you can save and then you can take heat in the form of exothermic reaction. So this is your thermal storage, correct? So these are your energy storage system types, broad. Then discussing the pumped hydro storage system. So what happens here? Basically, what we are doing, when we have extra energy, we are converting it into potential energy. And how we do, one basic idea is to store your water, pump your water at some height so that it attains potential energy, right? So this is one basic idea that is used in pumped hydro. Hydro is for water, right? Pump. So water is pumped at some height so that it has some head, and later it can be harnessed. So this is a pumped hydro storage system, right? Then in your pumped hydro storage system, if you have to define how efficient your system is, how do you do that? Okay. So a parameter turnaround efficiency is used to define that. So turnaround efficiency is nothing but your total energy output divided by total energy input. Okay. So this is basically your turnaround efficiency. Then is your compressed air storage system. So in your compressed air storage system, as the name suggests, you store energy in the form of compressed air. Okay. And you store energy in some reservoir or some aquifer. Okay. So what is an aquifer? So an aquifer is a body of permeable rock which can contain or transmit groundwater. Okay. So this is your aquifer. Right. So your compressed air storage system, one is your adiabatic and one is your hybrid. Now, what is the difference? So when you have extra energy, right? If you see your this power plant system, so when you have extra energy, what you do through your compressor, you get your air compressed, and you save it in some reservoir. Okay, but there is one point to note, that is when you compress air, it gets heated. Yes. So this heat at times is saved in some way. Okay. And at times it is not saved. Right. So what are the repercussions of that? So later when we have peak load, right? So this is you're compressing air at off peak load, right? When your load is not high, right? The availability of load is high, but the demand is not high. Okay. During that time, you have compressed this air. Yes. And when you have to expand it, right? So if the temperature of air in that case is high, so it will be more efficient. Okay. So if you save while compression, the air gets heated. So at times you save this heat, and at times you not. Okay. So if you are not saving this heat, then during compression, during expansion, you'll have to, by some external source, you'll have to give heat to this air. In that scenario, this whole system becomes hybrid system. Okay. And if you are saving your heat from compression, then it's your former case. I hope this is clear. Okay, so this is your compressed air storage system. So these were topics related to your lecture number 32. Necessity for energy storage system types. Electric storage. In electric storage, we have electric mechanical storage and then direct electrical storage. Then is your thermal storage in the form of your sensible heat, latent heat, and chemical reactions. In chemical reactions, specifically endothermic reactions. Then, moving on to questions. Whether this is correct or not. The statement talks about peak saving. So please read the statement and try to think about it. Sorry. Question number one, power plants are designed for constant load operations below peak load. So this looks something like this. Okay. This basically is your constant load. This section is for your peak load. Okay. This is when your demand is low. So when the demand is low at that time, you'll save the energy or store the energy. Yes. So what's the advantage of this peak saving basically is if you want to increase this constant load, the level of constant load, if you want to increase, in that case, the costs of the capital costs increase, right? Right? For the whole system. So in that case, you choose such load, right? Where the costs are not high. In addition to that, at times you can save the energy, and when the peak, you have peak load, during that time you can release that energy. Okay, or use that energy. Right. So this is a correct statement. So which of the following energy storage systems is based on kinetic energy? Four options have been given. Please try to think about it. First option is pumped hydro storage. Second is compressed air storage. Third is mass elevation. Fourth is flywheel. First option is your potential energy. Second again is your potential energy. Mass elevation again is potential energy. Fourth is flywheel. Flywheel is based on kinetic energy. In that case, fourth option is the correct option. I hope this is clear. Then we move on to next question. So I have told you what is turnaround efficiency is. So here combined efficiency of your pumped hydro storage system is turnaround efficiency. Whether this is correct statement or not. Turnaround efficiency. Is your total energy output to your total energy input. Okay, so difference between input and output basically is losses, right? So this seems to be a true statement. Yes. So answer is also A option. So this is a correct statement, right? So this was about lecture number 32. So this is your lecture number 33. The topics it has are necessity for energy storage, then thermal sensible energy storage. Just give me a second. So the topics are necessity for energy storage, thermal sensible energy storage, then pressurized water sensible energy storage. Okay. Then is your latent heat energy storage. Right. So necessity for energy storage is from the previous lecture only. Okay. This is lecture number 33. So there is thermal sensible energy storage. So for your Rankine cycle, when you save your thermal energy, in that case it is named as steam storage. Okay. So what happens is, here what happens is, when there is low demand, right? In that case, you'll have excess steam, right? So what you do to this excess steam, so this is bled at high pressure turbine. Okay. And then what happens? So this basically comes in your pressure water sensible energy storage. This topic basically. This topic. Okay. So this comes in your pressurized water sensible energy storage. So from here, what do you do to your extracted steam? your extracted steam goes to your accumulators. Okay. When the demand was low, the excess steam you bled from your high pressure turbine, and this extracted steam goes to your accumulators, right? Where it is condensed, and what it becomes is saturated pressurized water. It becomes this, right? And when the demand is high, or when the demand is at peak, so for the peak load, you pass it through small peaking turbine. So this way, your pressurized water, sensible water, and a sensible energy storage system works. So there was low demand at first. From there, we took excess steam. Okay. So excess steam from high pressure turbine we extracted, and this extracted steam is going to accumulators where it is getting condensed and pressurized. And this pressurized water then goes to your small peaking turbine, okay, for expansion during peak loads. I hope this is clear. After this, we have next topic is your latent heat energy storage. So, as we know what is latent heat, okay, the hidden heat. So, while changing phase, there is some energy that the material absorbs, right, which doesn't show up as increase in temperature, right? So, that basically is your latent heat. So, and in case of vaporization, we call it latent heat of vaporization, right? For energy storage, this latent heat can be used. Okay, so first we will provide heat, and then when this phase change takes place, it will have energy stored in it because it will be in higher state. And when we need energy from it, we will again bring it to lower state, right? So if we have moved it from liquid to gaseous state, So if we want to extract energy from it, we will change it from gaseous phase to liquid phase, and in this way we can use latent heat for energy storage purposes. Okay. So for your latent heat energy storage, what is an ideal material for that, right? One is your eutectic salt. I hope I have spelled it correct. So this eutectic salt is basically sodium fluoride plus ferrous fluoride, FeF2, and then also zinc chloride is also used. So this is about your latent heat energy storage. So these were the topics. Then we shall see questions. So question number 4, it states that the storage density of thermal energy utilized in the peaking turbine per unit volume of high pressure saturated water can be expressed in terms of 4 options have been given. So this storage density basically is this. Okay. Now, if we see our options, this is your this basically is your specific volume, and these are two enthalpies. So if you see your third option, that basically is the correct answer to this question. So this was based on this formula for your storage density. In case of your pressurized water sensible energy storage system. Then question number 5. I hope question number 4 was clear. Question number 5, true or false type of question. Please read the question. So it says that in a pressurized water sensible energy storage system, the higher value of time constant results in lower value of thermal turnaround efficiency. So whether this is correct or not, so this basically is a false statement. So there is one formula based on which for your pressurized water sensible energy storage system, based on which you will realize that your higher value of time constant results in higher value of your thermal turnaround efficiency. Okay, so in that case this is a false statement. So we will do numericals also, there we will see. Okay, So this is a false statement. More options have been given. Please read the question and try to think about it. The question is on latent heat energy storage systems. Which of the following compound is suitable choice for latent heat energy storage system? Option A is magnesium chloride, magnesium hydroxide. B is zinc chloride. C is sodium hydride. D is magnesium sulfate. So we have discussed this here. One is eutectic salt and one is your zinc chloride. So if you see the options for this question, B is the correct answer. Okay. This was question number 6. Then we have numerical questions from 6 to 7 to 9. So information for that has been given to solve those questions. Please note down the information. Question number 7 to 9. A power plant is designed for 1000 megawatt for its base load operation. It is integrated with a pressurized, water sensible storage system for which the thermal energy of 5000 megawatt hour has to be stored daily. Then accumulators 5-meter diameter are well insulated and have overall heat transfer coefficient of 7 in SI units or kilojoule per H dot meter square dot Kelvin. Okay. The maximum and minimum storage pressures are 20 bar and 2 bar respectively, while the storage time is 17 hours. Take the specific heat of water under storage condition as 4.35 kilojoule per kg Kelvin and peaking efficiency is 27%. Ambient conditions also have been given. Then some other data has been given in the table also related to two pressures, 20 bar and 2 bar. It's temperature and temperature related enthalpy and specific volume. Question then asks for thermal turnaround efficiency, but before getting the thermal turnaround efficiency, we'll have to do some basic calculations. So let's do that first. So question number 7 to 9. Given diameter is 5 meter, CF is 4.35 per kg Kelvin, then heat coefficient is this, then theta time for which your storage system will work is this, then is your peak efficiency, peaking efficiency is 0.27, 27%, and the thermal energy that is to be Total is 5000 megawatt hour. Ambient conditions, then at 20 bar, what do you have? T1 equals to HF1 equals to VF1 equals to. At 2 bar, what is the information given? T2 is specific volume is, then first is the average density. Average density rho f will be equal to half of 1 by EF1 EF2. Now if you calculate this, please calculate this. So if you will calculate this, this will come out to be 896.43 meter cube per kg. Okay. Then time constant you find, because later these will be of use. Yes. Then putting the values, 4.35 divided by 4 into 7. So if you calculate this, so this comes out to be 696.3. hours. Okay, so this is your time constant. Then we will take question number 7, which says that you give us thermal turnaround efficiency. So thermal turnaround efficiency, 1 minus this. So we have seen one true or false type of question based on this only in the previous questions. So this is the relation between your thermal turnaround efficiency and your time constant. Putting the values, so if you solve this, this will come out to be 0.95. So 0.95 will be the thermal turnaround efficiency of this sensible energy storage system. The total water volume of the accumulator at 20 bar is, so water volume you have to calculate now. So how will you calculate the water volume? Water volume you will calculate basically using specific volume data and your mass, water mass. And how you will calculate your mass? This will be stored energy divided by enthalpy difference. Now stored energy Yes, is basically your thermal energy. Okay, you multiply the number of seconds with it to get it into megawatt, right? Then 1000 divided by 0.27, which is peaking efficiency, then 0.95, which is thermal turnaround efficiency. Now, if you work this out, this will come out to be, this will be around 7.02 into 10 raised to power 10 kilojoules. So this will be your stored energy. Okay. Right. Then you find out mass of water equals to 7.02 into 10 raised to power 10 divided by 908.5 minus 504.8. So this will come out to be 7.02 into 10 raised to the power 10 divided by 8.5 minus 504.8. So this will come out to be around 1.73 into 10 raised to the power 8 kg. Now you can find out the volume equals to mass is 1.73 into 10 raised to the power 8 into 0.00. Specific volume is 0017 0011766. Now multiply this. So this will come out to be 203,551.8 meter cube, right? If you here, keep it as 9, 9 into 10 raised to the power 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 9 into 10 raised to then it will be what? Then it will be 204610.74 meter cube. Okay. So this is your answer to this question. I hope this is clear. Then we will take a short break after this. Okay. The next question we will do after this break. Okay, so we can continue with the session. So question number 9, it says that accumulator, if an accumulator vessel is ruptured at 20 bar, then the amount of minimum energy released is. So if the accumulator vessel ruptures, okay, then the enthalpy or the energy release can be calculated from your enthalpies, right? If you see, let's keep this. So HF at infinity and HF at 20 bars. From there you can calculate this. Okay. So minimum energy release, E minimum is equal to E stored minus E ambient. E stored is EHF at 20 bar minus HF infinity. So this is HF 20 bar, HF infinity. So this will be this in kgs. And this is 908.5 minus 293. Now calculating this will come out to be, so this will come out to be 1.07 into 10 raised to power 11 kilojoule. Okay, so for question number 9, in that case, it will be 1.07, the fill in the blank. So this was it about lecture number 33. Then let's see lecture number 34. Yes. So here we have This is from previous lectures. Flywheel energy storage system, electrical battery storage, magnetic energy storage, chemical reaction storage, hydrogen energy storage. So briefly, let's see the topics. So first is your flywheel energy storage system. So this is based on first of all kinetic energy, right? And there are two modes here. One is your charging mode, one is your generation mode. So what happens in your charging mode? Your motor adds energy to the flywheel, the extra energy. Okay. And in the generation mode, your rotor coasts the generator. Okay. So this is used during peak loads. So what happens in your this electrical battery storage system? So lead acid batteries have been discussed. So in lead acid batteries, so in batteries for that matter, you have one is anode and one is cathode. At anode, you have oxidation taking place. At cathode, you have reduction. Okay. Here, lead acts as anode and lead oxide acts as cathode. Okay. So if you see the reactions taking place, so when lead plus sulfate ions, lead sulfate plus two electrons. Okay. This basically is your oxidation. Because here you are getting two electrons. Then is your at your cathode lead oxide plus this plus electrons. So this gives rise to this is your reduction reaction where your electrons are used to have the reaction. And the electrolyte here used is what? Dilute form of your sulfuric acid. Okay, so these sulfate ions and these H positive ions are coming from this electrolyte only. right? Then is your storage, magnetic energy storage. So what happens in your magnetic energy storage? Basically, you take help of superconductivity. So you will save your electricity in such a coiled material, okay, that is in its superconductive state. And because there is no resistance in your superconductive state, so this saves losses. And when eventually we need this saved energy, we can anytime harness it. Okay, this basically in the form of your in the magnetic form. So this is your magnetic energy storage. Then is your chemical energy storage. So two type of reactions. So what is endothermic reaction? Endothermic reaction is one where to make the reaction possible, you use heat with the reactants of the reaction. And in your exothermic reaction, when the reaction takes place, it releases heat or energy. Okay. So in endothermic reaction, you give heat. So we choose one such reaction which is reversible. Here, when we have energy, excess energy, we get our endothermic reaction done. Okay, and then when we want to use this energy, we move in reversible path, in the reverse path, where it will, in the reverse path, it will give heat because it's exothermic in that case. So this basically is your chemical energy storage. Then is your hydrogen energy storage. So hydrogen, first of all, is a clean fuel. Okay. So hydrogen, when oxidizes, gives rise to water. That's why it's a clean fuel, right? But also it is highly inflammable. So storing Hydrogen is a task in itself. So what we do in that case, we use it either in the form of ammonia or metal hydrides. And from there we get hydrogen whenever we require it. Okay. So this is your hydrogen energy storage. So briefly I have discussed this. Then moving on to questions. Question number 10, in a lead acid, battery dash and dash act as anode and cathode respectively. Lead, lead oxide, lead oxide, lead, lead, lead hydroxide, lead hydroxide, lead. So lead, I have written the reactions also involved. So lead acts as your anode where oxidation takes place, and lead oxide as cathode where reduction takes place. So A is the correct option. So this is from your magnetic energy storage system. A coil that gives maximum dash to dash ratio is known as Brooks coil. Inductance is denoted by L, volume is V, mass is M. So which maximum ratio is related to your Brooks coil? Either this is L by V or V by L or L by M or M by L. So if you go through your lecture 34, this video, you'll see that the correct answer is A. Okay. L by V is maximum. When L by V is maximum, inductance to volume ratio. In that case, that is known as Brooks coil. Okay. So A is the correct option. Then moving on to next question. In a chemical reaction storage system, an endothermic reaction known as dash is used to store energy. So endothermic reaction, also known as reformation. Okay. The exothermic reaction, also known as methanation, is used in your chemical reaction storage system. So A is the correct answer to this question. Alright. So this was question number 12. And then we have come to the end of this session. So in that case, I can conclude today's session. So there were total 3 lectures, all on your energy storage system. First, we saw our electrical storage system, right? So we got to know that there are two storage system. One is electrical, one is thermal, right? And later we saw there are other types also, like this hydrogen storage and then magnetic storage, right? Broadly, there is one electrical, one is your thermal. And in electrical, we saw pumped hydro storage system, which was based on potential energy, and then compressed air storage system, which again was on the potential energy. Then in lecture number 33, we saw thermal energy storage systems, where we saw pressurized water sensible energy storage. Okay, where we the extra high pressure steam when the load requirement is less and the steam avail, availability is in excess. In that case, we blend it, right? And at the accumulators, we condense it, and later we use this condensed steam when the peak load requirements are there. Okay, and then here we saw latent heat energy storage also. Okay, so which compounds we use? One is zinc chloride, and then is eutectic salt for your latent heat energy storage, right? Then in lecture 34, we saw kinetic energy based energy storage system, which is flywheel. Then electric battery for energy storage, where we focused on basically lead storage batteries, but there are other batteries also. Then was superconductivity based magnetic energy storage. Then recently we saw chemical reaction storage, and at last we saw hydrogen energy storage system. Okay, so this is it about your week number 12. Also, the last week of this course. So we have come to the end of this course, right? So I hope this course was a learning experience for you all. And though we have completed our sessions related to each week, but one extra session I'll be taking, okay, where I'll just briefly discuss the whole course and the topics covered in it. Okay, so that I'll be taking tomorrow only from 6 to 8 p.m. So that will be a course concluding session. Okay, so this is it about today's session. Thank you.